Okay, so now we're in a position to frame the eigenvalue problem, including the the generalized eigenvalue problem, in terms of an optimization problem on a matrix manifold. Okay, so the eigenvalue problem as an optimization problem. And this entails showing that a particular cost functional actually has minimizers which are related to what you want. Okay, so let me state the following proposition. Okay, so let A and B be symmetric. By n matrices, and then as before, B has to be positive definite. Okay, and then let's order the eigenvalues. So let lambda 1 be less than or equal to lambda 2. Be the eigenvalues of the matrix pencil. Okay, and then we consider what is called the generalized Raleigh quotient. Okay, and it's given as follows. F is a function of y is equal to the trace of y transpose AY multiplied into y transpose BY inverse. And this is defined on the set of all n by p full rank matrices, right, which basically are just p-dimensional subspaces, okay, or which generate p-dimensional subspaces more precisely, right, then the following is true. The following statements are equivalent. So the first of which is that the span of the span of the the value y, which minimizes this Rayleigh quotient, is going to give you the leftmost invariant subspace. Is A, well, A leftmost. And the non-uniqueness has to do with the fact that the eigenvalues could have multiplicity. Okay. So put another way, if the eigenvalues have multiplicity, its eigen p is such that it splits eigenvalues of the same value, right? Then there could be more than one leftmost invariant subspace associated with that. Okay. So the second thing is that y star, which is again the value of y which minimizes this cost function, right, is a global minimizer that's this function. Let's just call it star overall n by p full rank matrices. Okay, the third condition. So the point is that all these three are equivalent. F of y star is equal to the sum from I equals 1 to p of lambda I. Okay, so, all right. So let's prove the following. So we're going to simplify the proof a little bit by assuming that you actually have strict inequalities in this ordering. It doesn't really matter. You know, you can prove it even if that's not true, but it makes your life a little bit simpler. So we assume for simplicity actually, all we really need is that lambda p is less than p plus 1. Okay, so this basically eliminates the case where, you know, it's like there's some non-uniqueness in this leftmost invariant subspace. Okay, so if lambda p is strictly less than lambda p plus 1, then this leftmost or p leftmost invariant subspace of AB is actually unique. Okay, but the result holds without this assumption as well. Okay, but as I said, it's like it just makes your life easier. It's like because makes this thing unique, right? Yeah, so that makes your life easier. Okay, so let V be a n by n matrix with the property that it is B orthonormal, V transpose B V is equal to the identity, the n by n identity matrix, and V transpose is, V transpose AB is going to be the diagonal of eigenvalues. Okay, where you have this ordering. Okay, so again, it's like this V is basically the you know, it's like the n by n matrix consisting of the eigenvalues. It's like associated, the eigenvectors associated with eigenvalues. It's like ordered in this way, right? And this always exists. Always exists. Right. And the reason, of course, is because we've assumed this symmetric positive definite case. It's like where A and B is symmetric and B is also positive definite, right? And that gives you then this complete set of eigenvectors, amongst other things. Okay, all right. So let's say we have Y be set of n. So Y is an n by P matrix, and I let Y equals to V times some other matrix M, and I can always do that. Okay, so now we'll use some properties of this V. Okay, so Y transpose BY yes, Y transpose BY is the identity. Okay, actually, let me do that again, right? y is Vm. Okay, so that's M transpose V transpose B Vm. This is going to be the identity n by n. Oh, okay. All right, but we're going to use the fact that y is right. So it also is the case that y transpose by is the identity matrix, p-dimensional identity matrix. Okay, so it has to be that this implies that this is IP. This implies that okay, so I've used this condition here. So this implies that M transpose M is the p-dimensional identity matrix. Okay. All right. So that makes my life a little bit simpler. Okay, because this thing shows up here. Okay. So maybe let me write down this functional f of y equals the trace of y transpose a y, y transpose b, y inverse here. Okay, and I'll leave the equivalent statements for now. Okay. So, okay, so the trace of y transpose a y equals to the trace of M transpose the diagonal lambda 1 to lambda n of M. Right, this just comes from the fact that y transpose a y is equal to M transpose V transpose a V M. And then this is just the diagonal lambda 1 to lambda n. Okay, so that's just a calculation coming from the substitutions. All right, and so this trace gives you the sum of the diagonal entries of this matrix. Okay, so you can write down what that is. So it's the sum from I equals 1 to n of lambda I, then the sum j equals 1 to p of mij squared. Okay, so I can write this as the sum from I equals 1 to p of lambda p plus sum from I equals 1 to p of lambda I minus lambda p mij squared plus the sum from I equals to p plus 1 to n of lambda I minus lambda p mij squared. Okay. All right, so basically what I'm doing is, sorry, let me take the j here. Okay, so I'm basically switching the order and take the j, it's like I'm putting the i's. Okay, basically swapping the order and check out the summations. All right, and then breaking up the sum from I equals 1 to n to 2 pieces. All right, and then just yep. And I'm also using the fact that M transpose M is the IP, right? So here we used the fact that M transpose M is IP. Well, I mean here generically, right? Okay, all right. So this gives me the sum from j equals 1 to p of lambda I plus the sum from I equals 1 to p of lambda p minus lambda I times 1 minus the sum from j equals 1 to p of mij squared plus the sum from j equals 1 to p, the sum from I equals p plus 1 to n of lambda I minus lambda p mij squared. All right, so since the second and the last terms are non-negative, right? So since the second and last terms are non-negative, right? That means that this thing is greater than or equal to just this sum here. The trace of y transpose ay is greater than or equal to the sum from j equals 1 to p of lambda I. Okay. And then you only get equality if those two terms vanish. And in particular, this only happens if and only if the sort of n minus p by n by p, lower part of m vanishes, which basically means that the p by p upper part of m is orthogonal. Okay, and this means that y is equal to Vm spans a p-dimensional leftmost invariant subspace. Of AB. Okay. All right. So so that proves it's like what we need to show. All right. Again, it's like the bottom line, if you will, is that if you want to characterize the p-th leftmost invariant subspaces, then you construct this generalization that's like of the Rayleigh quotient, and then you want to minimize it over the space of n by p full rank matrices, right? And one can check that this reduces. It's like to the usual Rayleigh quotient in the appropriate limiting cases. So let me just stop here for now.